All right, another one for you. This is chapter 8, hypothesis testing and testing a claim about population mean. So in this section, basically we present methods for testing claims about a population mean through hypothesis testing. So part 1 deals with the very realistic and more commonly used case in which the population standard deviation sigma is not known, okay? Part 2 discusses the procedure when sigma is known, which is a very rare scenario. You're going to have somebody tell you that it is known, or that you have data that would indicate it is known. Okay, so more commonly, population standard deviation is not known. So part 1, when sigma is not known, we use the student t distribution, and therefore it's a t-test that incorporates the student t distribution. The test statistic, you should write this down in your notes. T is equal to x bar minus mu x bar divided by s divided by the square root of n. So one thing to note is in this case, you see s and not sigma because sigma is not known. So we're going to use the sample standard deviation, which again, sample standard deviation is s right here. Mu x, in other words, the population mean, is more commonly denoted as just mu. So you might see this expressed as x bar, in other words, the sample mean, minus mu, not mu of x bar, okay? Something to note. Again, n is the sample size and s is the sample standard deviation. Two of the requirements, the sample is from a simple random sample, and then you need an either or clause here. So either or, both of these conditions is satisfied, the population is normally distributed. So in other words, for which you took the sample from is from a normally distributed population, or the sample size is greater than 30, or both can be met. Running the test, we can either do the p-values or we can do the critical values. If you're doing p-values, you'll find out that you want to use technology, or you're going to use the student t distribution in the table A-3 with degrees of freedom n-1. If you do the critical values, use student t distribution with degrees of freedom of n-1. Again, if you do the p-value method, you're going to compare it with alpha. That's basically how we would solve that. If you want to go back and review section 8.2, that'll tell you again the general rule of how we want to do that comparison of alpha to the p-values. Yeah. But again, a reminder of the important properties of the student t distribution. We already covered this, right? But basically, the student t distribution has different shapes for different sample sizes. If you remember, it has tails that can be fatter based on the sample size, okay? It has the same general bell-shaped curve as the normal distribution. It also is symmetric in that extent. It is wider, its wider shape reflects the greater variability that is expected when S is used to estimate sigma. The student t distribution has a mean equal to 0, so that's why we use that converting of that test statistic. The sample standard deviation of the standard deviation, sorry, of the student t distribution varies with the sample size and is greater than 1. As the sample size n gets larger, the student t distribution gets closer to the standard normal, right? I think you remember that from one of the graphics I showed you before in chapter 7. So feel free to review the chapter 7 material. So the example I'm going to use here is basically about the radiation emitted from a sample of cell phones. So use a 0.05 level of significance, so that's our alpha, 0.05, to test the claim that cell phones have a mean radiation level that is less than 1.00 watts per kilogram. One thing that's really important to note when you're doing these story problems is to figure out anytime they say test the claim, you should really be cued in, and then you should look for a word that says the proportion, the percentage, the mean, the standard deviation. In this case, you see it says mean, and you obviously know we're doing section 8.4, which is mean, so you should know that we're dealing with that, but it's really important to understand how you would digest that. The other piece of information that's important here is less than 1.00 watts per kilogram. You're going to know that's how it's going to help us set up our hypothesis, right? So in other words, our claim is that mu is less than 1.00. To make that false, we would say greater than or equal to 1.00 watts per kilogram. Okay, there are our data values, the summary stats from it. If you want to run it, you can run it as a list real quick on your calculator and have it do one variable stat. It'll tell you the standard deviation and x bar. Some of the requirements you should do before you go ahead and do your hypothesis testing is you want to make sure it came from a simple random sample and that the population either is from a normally distributed population, or I mean the sample came from a normally distributed population, or that the sample size is greater than 30. In this case, the sample size is very small, it's only 11, so we should do a normal quantile plot because that way we can see whether it came from a normal distributed population. In this case, it looks like there's no apparent pattern, and it does kind of follow that line. To me, it looks like you have probably 3 groups of cell phones, maybe one brand and another brand and another brand. I don't know for sure, but I wouldn't be too I wouldn't waste too much time scrutinizing over those small details, but it looks kind of like it would come from a normally distributed population. Step 1, identify the claim, write it in symbolic form. Mu is less than 1.00 watts per kilogram. Make the alternative to that claim. In other words, what would make that false? Well, greater than or equal to would make that false. Now write that in your basically hypothesis, your null and alternative. So in this case, our alternative is our claim, which is great. Mu is less than 1.00 watts per kilogram. And our null is that it equals 1.00 watts per kilogram. Our hope is maybe that we reject the null in favor of the alternative. But we'll see what happens. Step 4 is pick a level of significance. In this case, it was stated that it was 0.05. Step 5, because the claim is about a population mean, mu, the statistic most relevant to this test then is the sample mean x bar, okay? So calculate the test statistic and then find the p-value. So if we go and calculate the test statistic, which I would recommend you guys take your calculator out, make sure you put this in correctly. Remember your orders of operations, parentheses. You'll end up with negative 0.486. And if we were to put that on a graph, we can see that's where basically our test statistic lies, is right here. And then if we were going to do the critical value method, we would find basically the cutoff and the left tail that would separate 0.05 from 0.95. And anything in this red region or pink region would be considered the critical region, i.e. the rejection region, where we reject the null hypothesis. In this case, it lies in the fail to reject region, and therefore we fail to reject the null hypothesis, that it's probably equal to 1.00 watts per kilogram. Now, the p-value method, you're going to want to use technology. You can make an estimate about it with the table, but technology is going to be your friend. You can use your calculator to do this if you want. You can use StatCrunch, you could use Stata, you could use SAS, SPSS, any of those programs. The important thing is to know how you want to construct it, though. So in this case, similar to what we had before, you see that this t is going to be equal to your test statistic. This p right here is actually your p-value, not your proportion, but your p-value. You have x bar, and you have sx, and then n is being your sample size. In this case, the p-value is 0.3191, which is greater than the alpha value, so therefore we fail to reject the null hypothesis. Okay, now step 8 is always take whatever information you have in terms of whether you fail to reject or reject the null hypothesis and convert it back to non-technical terms that somebody could understand, that is maybe not in the class. So because we fail to reject the null hypothesis, we conclude that there is not sufficient evidence to support the claim that cell phones have a mean radiation level that is less than 1 watt per kilogram. In other words, we can't support that claim that cell phones emit less than 1 watts per kilogram. It's probably more likely they could be equal to 1 watts per kilogram or more. Finding p-values, if you want, you should take the table out and see if you can find these, right? Assuming that neither software nor a TI-83 or 84 plus calculators available, use your table that you have, table 8-3. I'm going to pause the video for a second and re-record here in a moment. Okay, so we should be resumed recording here. Sorry, I had to grab my table and I didn't want the pause to be too long. So in a left-tailed hypothesis test, the sample size is n equals 12, which means our degrees of freedom would be 11. That's correct. And now we want to figure out where that test statistic of negative 2.007. Keep in mind the distribution is symmetric, which means you can look at the positive numbers and think about where that would lie as well. Remember, it's one-tailed. And in this case, I would say that the p-value lies between 0.025 and 0.05. And here, I will put up the smaller video on the far right of the screen. Oops, let's go back. All right, so now that we have that up here, right, this is your table 8-3, right? some of the things that you should be really familiar with. I'll zoom in just a little bit more. So we found the degrees of freedom was 11 because we're dealing with n is 12. And now if we imagine this was the negative side of the distribution, we'd see that the value of negative 2.007 would lie between negative 2.201 and negative 1.96. Keep in mind, this is only doing the right side or the positive side of the distribution. And we know it's one-tailed because it's just left-tailed, which means that p-value probably lies between 0.025 and 0.05, okay? All right, let's do B now. So it's a right-tailed test, which means it's one-tailed. So we're gonna be looking at the area in one tail for sure. And the sample size is 12 again. So that means degrees of freedom is 11. So we're still looking at that same line right here. And it looks like 1.22 is actually less than, oops, you can't see that, 1.363, right? So that means the p-value is probably greater than 0.1. Now, if you're at all curious about this, I would sketch this out, put the test statistic there, and then figure out what this means in terms of the area. And you'll see that it lies closer to the middle, which means it would have a higher p-value, or basically higher probability. All right. C, in a two-tailed hypothesis test, the sample size is n equals 12, and the test statistic is negative 3.46. So degrees of freedom 11. Looks like I see 3.106 is the largest value I'd have out there. And to me, even if we doubled that value, it's still going to be less than probably 0.01. So the p-value is less than 0.01. And if you want to do a quick sketch of those, so let's sketch those out just to make everyone a little maybe more happy, just in case you're worried about that. Since I have this super zoomed in, it's harder to put my thing on there. So this is a left-tailed test, means it's on this side of the distribution, right? And we have t is equal to negative 2.007. Keep in mind, right, in the middle of the distribution, t is equal to 0, right? These are all the positive values. And in this case, I had found, grabbing another color, that 11 degrees of freedom, we have this 2.201 and 1.796. And so if we were to put those in here, 1.796 maybe here, and negative, by the way, negative 0.201 is here. So that means basically this area to the left of that negative 2.201, if you're looking at it, is 0.025. And if you were looking from here over this way, it would be less than 0.05. So in other words, the p-value lies between that bounds. So in other words, the p-value lies, so you might say 0.025 less than the p-value, which is less than 0.05. So you might write that as basically being the p-value for a range of values. So again, just trying to make sure you understand how you interpret those, okay? Now, if we go to B, oh, stop that shaking right now. So B, we sketch it out. It's a right-tailed test, and we have 1.22, 22. And if you were to look at your table again, 11, 1.22, we see 1.363, right, is right here, 1.363, and that would correspond to an area of 1.10 in the tail, which other words, that means the p-value is greater than 0.1. Okay? Because if you think about the test statistic, remember, the area that's to the right of it is what its p-value is, if it's one-tailed. If it's two-tailed, you take that area and then double it, okay? And that's what I'll show you here in a second. So for C, we'd be finding that negative 3.456. By the way, this is not drawn to scale. That is basically our test statistic, right? And so we want to find the p-value associated with it. If we look at our table and find 11 degrees of freedom, and we find the negative 3.106 corresponds to an area of 0.0005 in the left part of the tail, or we can think of the area in two tails as being 0.01 because it's doubling it for us. Basically, that means that if we have that negative 3.106, that means the area on both sides of 3.106 would sum to 0.01. In other words, this p-value right here associated would be less than 0.01. Okay? That's how you basically do those ones, okay? If you have more questions like that, please come see me during office hours or see me during my virtual office hours, and I'd be happy to go over any kind of problems like that. All right, confidence interval method. We can use a confidence interval for testing a claim about a mean meal. For a two-tailed test with a 0.05 significance level, we construct a 95% confidence interval. For a one-tailed test, a 0.05 significance level, we construct a 90% confidence interval. That's basically because the way that we've constructed confidence intervals, we've done like T alpha over 2. And so if you have a one-tailed 0.05, you do 90%, you're actually doing half of the 90% of the alpha of 0.1, and you get 0.05. And that's why we say that's the significance level. Either way, if you were going to do the same test for the cell phone, basically what you're testing to see is if mu, in other words, let's go all the way back here. Oops, that was too fast. Bear with me a second. We'll get back to it. I'm going the wrong way, that's why. So there is our null hypothesis. Mu equals 1.001 per kilogram. And so if we go back to this problem now right here, does 1.00 fit in there? And in this case, yes, it does, which would mean then that we would fail to reject the null hypothesis because the null hypothesis is contained within that confidence interval, right? So we cannot reject the null hypothesis. In other words, we fail to reject it, right? So we do not have sufficient evidence to support the claim that the mean radiation level is less than 1 watts per kilogram. Okay, part 2, when sigma is known, by the way, but this is a very rare case. This is not usually known. In reality, it's very rare that you'd actually know this, okay? The one thing that's different, instead of using a t-test, we're gonna use the standard normal distribution instead, but it's basically the same. The only thing that changes is that instead of S, we're now using sigma, and instead of using the t distribution or the student t, we are now using the standard normal distribution. So everything's basically the same, the way we test and do all that stuff. The only difference now is that we're gonna use sigma because we know it, and you have the standard normal distribution. Your test statistic. So we go through and do that. You can find that p-value pretty easily, I think, on your own. But you'd find that negative 0.43. It's a left-tailed test. So just to put it up on the screen. I'll put this up on the screen, sorry. There we go, and make it a little bit bigger. So if we find that negative 0.4 and we go over to 0.43, we'd see that 0.336. Remember, this is left-tailed, which means this reads cumulative from the left, which means we can take that value and use that straight up. And so 0.3336 is the p-value associated with it. So again, we would fail to reject the null hypothesis and reach the same exact conclusion we reached before. Because we're comparing it to the alpha value. Again, if you're at all confused on that, I would recommend you review section A-2, which is basically the basics of hypothesis testing. Okay. Move that smaller again. And that's it for 8.4. Trying to keep these short and sweet. Feel free to stop in during office hours and ask me any questions you might have.